The blue whale. I mean, it's just the biggest animal ever, right?
Right.
Bigger than any dinosaur we know of.
Absolutely colossal.
And that image everyone knows, the one you see in documentaries, its heart being like the size of a small car.
Yeah, maybe an old VW Beetle or something similar. That's the classic comparison.
That's an incredible visual, isn't it?
Yeah.
It really hooks you in, tries to give you some sense of just how enormous this animal is.
It really does. It's a powerful hook, no doubt about it. A great starting point for thinking about, biological extremes.
But as we always try to do here on the deep dive, we want to go beyond that initial hook, right?
Exactly. Our goal today is really to dig into the science, to separate that popular analogy from the actual hard data.
So figure out how big it really is.
Yes, and also understand why the real measurements might differ from the popular myths, and how this incredible engine actually works to power the biggest creature on Earth.
Okay, let's definitely unpack that, because the car-sized idea often comes with another figure, doesn't it? The weight.
Oh yes, the weight.
You hear these huge numbers thrown around, 600 kilograms. Sometimes people say even more, like a ton.
Right. Those numbers are definitely out there in the popular consciousness.
So what are we actually looking at when scientists get their hands on a real specimen? What's the actual weight class here?
Well, the scientific data, the stuff that's carefully measured and preserved for study, it tells a rather different story.
Different how?
That 600 kilogram figure, or even higher numbers, they likely stem from older estimates, maybe speculation, or perhaps measurements from very fresh carcasses.
So maybe including all the blood and fluids still inside.
Exactly. Think about it. A massive organ, still engorged with potentially hundreds of liters of blood, plus surrounding tissues and fluids. That adds a lot of temporary weight.
Okay, that makes sense. So what happens when it's prepared properly, like for a museum?
Well, when you meticulously extract and preserve it to scientific standards, the weight comes down considerably.
And do we have a good example of that?
We do. Probably the most famous one is the heart from that blue whale that washed ashore in Newfoundland back in 2014.
Oh, I remember hearing about that one. That was a huge effort, wasn't it?
A massive undertaking. It took, I believe, 3 days just for the extraction process, a real logistical feat.
So, the moment of truth. After all that work, what did the preserved heart actually weigh?
Approximately 180 kilograms.
180 kilos. Okay. Now, that is still incredibly heavy, like easily the weight of 3 grown men.
Oh, absolutely. It's enormous by any standard.
But it's a far cry from 600 kilos, isn't it? That's less than a third of the commonly cited figure.
A very significant difference, yes.
So why do you think that bigger, maybe sexier number persists so strongly in popular science?
Well, frankly, the bigger number does a better job of conveying the sheer, almost unbelievable scale of the animal. It grabs attention.
But it's misleading, ultimately.
It is, if you're talking about the functional muscle mass. What the teams, like the one at the Royal Ontario Museum working on the Newfoundland heart, did was crucial.
What was their process?
They carefully drained the blood, cleaned the tissues, and measured the actual muscle, the functional organ itself.
Gotcha. And you said it was large physically, too, not just heavy.
Oh, yes. That preserved Newfoundland sample, when you included the aorta coming off the top, measured nearly 2 meters in length.
Wow. Still absolutely huge.
Definitely massive.
Yeah.
But it's a focused, powerful muscle, not just a giant fluid-filled bag. And that distinction, preserved muscle versus a fresh, blood-engorged organ, is really key for scientific accuracy.
I really appreciate you making that distinction clear. It shows why just grabbing the first flashy number isn't good enough.
Precisely. Rigor matters.
But okay, even at 180 kilograms, that heart is still, biologically speaking, just absurdly large compared to ours, for instance.
No comparison, really.
So what's the biological reason? Why does the blue whale need a heart on that kind of scale?
It comes down to some pretty fundamental principles of physics and biology. Specifically, what we call allometric scaling laws.
Scaling. The idea that things don't just get bigger proportionally, right?
Exactly that. It's the classic square cube law challenge. When an animal gets longer, its surface area increases roughly by the square of that length increase.
Okay.
But its volume, and therefore its mass, increases by the cube of that length increase.
Right, so if you double the length,
You multiply the mass by 8 times, 2 cubed.
8 times the mass just from doubling the length. That's huge.
It is. And that's where the big challenge for the internal systems comes in.
I've often wondered about that. Nature is usually so efficient, isn't it? Why can't it find a biological shortcut? Why does the plumbing, the circulatory system have to scale up so drastically?
Because that system has an enormous job to do. It's not just serving the tissues right next to the heart. It has to push oxygenated blood out to every single cell across truly vast distances within the whale's body.
Like plumbing a small house versus a giant warehouse complex?
That's a pretty good analogy, actually. The sheer volume of tissue and the distances involved demand a massive infrastructure. The blue whale needs that incredibly powerful circulatory system, and the heart is the pump at the center of it all.
So the 180 kilo engine is basically the minimum required size for the job.
It's what's needed to efficiently pump hundreds of liters of blood with every single beat, to get oxygen out to all those immense muscles that propel it through the oceans.
Okay, framing it as an engineering requirement really helps put the size in perspective. It's less about breaking records and more about meeting needs.
Precisely. Form follows function, even on a colossal scale.
So let's shift from why it's so big to how it works. Is this giant pump fundamentally different in its operation compared to, say, a human heart, besides the obvious volume difference?
Well, anatomically, the basic blueprint is surprisingly similar. It's a 4-chambered muscle, just like yours or mine or any other mammal's heart.
2 atria, 2 ventricles.
That's right. But its specialized size and geometry mean it employs a different performance strategy. It's built for volume and endurance rather than, say, a really rapid beat rate.
So it pumps huge amounts of blood, but maybe slower.
Relatively slower per beat compared to a smaller mammal, yes. It's moving massive quantities with each contraction.
And what's really amazing is how it performs under pressure, right? Like during those incredibly deep dives they do.
Yes, that's where the efficiency truly shines. To conserve oxygen and energy deep underwater, the blue whale has to dramatically slow down its metabolism.
And the heart rate reflects that slowdown.
Absolutely. It's one of the most striking adaptations. Researchers have actually managed to measure this.
How? Attaching an ECG to a blue whale sounds challenging.
It is. It involves using specialized suction cups to attach sensors, basically an electrocardiogram setup, to the whale's skin before it dives. A real feat of engineering and fieldwork.
Incredible. And what did those ECGs reveal?
They show that when the whale is resting or diving deep, its heart rate can drop to astonishingly low levels.
How low are we talking?
Sometimes as low as just 1 or 2 beats per minute. Maybe even less frequent, like 1 beat every 10 seconds in some cases.
1 beat every 10 seconds.
Yeah. It's almost hard to fathom.
That sounds incredibly slow, almost like suspended animation.
It's the ultimate example of biological energy saving. That incredibly low rate is absolutely critical for making those long dives possible, conserving precious oxygen.
But it can't stay that low all the time, surely.
Oh, absolutely not. The system is incredibly dynamic. When the whale needs to surface, breathe, or maybe accelerate quickly to feed or escape something.
It needs power fast.
Exactly. And the heart rate can spike rapidly. It can jump up to maybe 25 or even 30 beats per minute to meet that sudden high metabolic demand for oxygen.
So it's like an engine that can idle almost down to nothing, but then roar back to life instantly when needed.
That's a perfect way to put it. Incredible flexibility.
Okay, let's loop back to that initial comparison then. The car. Given everything we've discussed, the real weight, the scaling, the slow beat, is comparing the heart to a car ultimately just misleading.
Misleading. I wouldn't say entirely misleading, but it definitely lacks nuance.
How so?
Look, the comparison does a fantastic job for public outreach. It conveys the absolute size, which is genuinely mind-blowing and sparks people's imagination. That has real value. But it's crucial to add the context of relative size. While the heart is huge in absolute kilograms and meters, if you look at its weight as a percentage of the whale's total body weight, it's actually quite similar to the heart-to-body weight ratio found in many other mammals, including much smaller ones.
Interesting. So nature scales up the engine, but it keeps the relative proportions roughly the same.
Exactly. It's huge because the animal's huge, but it's not disproportionately large for its body size. It demonstrates this underlying principle of efficient and economical biological design.
Build it just big enough for the job, but no bigger than necessary.
That seems to be a fundamental rule in biology.
Yeah.
And while we're talking analogies, maybe we should quickly address that other popular myth.
Which one is that?
The idea that a human can swim down the blue whale's aorta.
Ah, yes, I've heard that one too. Like it's a giant water slide.
Right. It's a fun image, great for fiction, but scientifically, Not really plausible.
Why not? The aorta must be massive.
The diameter is certainly large, yes. But the aorta isn't just a passive pipe. It's an incredibly thick, muscular, elastic artery. It's surrounded by other tissues, and it's actively pulsing with blood pressure. It's not designed for human exploration.
Okay, so we can keep the wonder, but maybe ditch the aorta water park fantasy.
Probably wise, yes. Embrace the awe, stick to the facts.
Now, thinking about getting those facts, you mentioned the huge effort involved in recovering and preserving that Newfoundland heart. 3 days, specialized teams, massive resources.
A monumental task.
Why go to all that trouble? Beyond just having a cool, giant heart in a museum, what's the real scientific payoff? What's?
This is where it gets really valuable for modern science, actually. These preserved hearts are like biological treasure chests.
How so? What can they tell us?
They offer incredibly detailed data on the heart's actual structure. Not just the overall weight, but things like the thickness of the different chamber walls, the specific elasticity of the aorta's tissue, the condition of the blood vessels.
So really fine-grained anatomical detail.
Exactly. And this detailed structural information gives us a vital baseline for understanding the general health of that particular animal before it died.
Okay, I see. And that baseline can then tell us about?
It allows researchers to start drawing conclusions about how pressures in the ocean environment might be impacting marine mammal physiology more broadly.
What kinds of pressures?
Well, think about chronic stress. If blue whales are constantly exposed to high levels of underwater noise pollution from shipping, for example,
Could that affect their hearts?
we might expect to see physiological changes over time. Perhaps changes in heart muscle tissue that could indicate hypertension or chronic stress, similar to patterns we recognize in humans under prolonged stress.
Wow. So the preserved heart becomes almost like a diagnostic tool, not just for the whale, but for the health of the ocean environment it lived in.
In a way, yes. We can also study tissue samples for contaminants, look at the impact of pollution on tissue health. It provides a tangible link between the environment and the animal's internal biology.
That's fascinating.
And it connects back to public awareness, too. That really engaging, easy-to-grasp fact, the sheer size of the heart, even the slightly mythologized version, becomes a powerful educational tool.
How does that work?
It highlights the majesty, but also the potential fragility of these massive marine ecosystems. When the public becomes aware of and fascinated by these incredible sensitive creatures.
It creates more support for protecting them.
Exactly. It builds pressure to address threats like noise pollution, plastic pollution, ship strikes, and any potential for illegal hunting. We use the awe generated by the scale to hopefully compel conservation action.
So understanding that it needs that super efficient, slow-beating heart helps us grasp how sensitive it might be.
Precisely. When you realize this animal operates on such fine margins, needing an engine that can idle down to 1 beat every 10 seconds just to survive its dives, you get a better sense of how disruptive human activities in the ocean could potentially be to its energy balance and overall health.
This really has been a deep dive, hasn't it? We went from that initial, almost cartoonish image of a car-sized heart,
A powerful, evocative visual,
acknowledged where the popular numbers likely came from, and then zeroed in on the scientific reality.
which is arguably even more impressive.
An incredibly efficient, roughly 180-kilogram engine, driven by those fundamental scaling laws and capable of that unbelievable dynamic range from near standstill to full power.
The blue whale heart really is just a profound testament to nature's ability to engineer effective solutions on a truly colossal scale while sticking to fundamental biological principles.
And science helps us appreciate the reality behind the wonder.
It defines that space between our sort of wildest imaginings and the actual biological facts. It confirms the wonder, but refines the numbers and the understanding.
A perfect summary.
And maybe a final thought for you, the listener, to take away. We marvel at this heart's ability to conserve energy, to operate at almost zero power during a dive.
Yeah, that slow beat is amazing.
But then consider the instantaneous power it must deliver the second that whale decides to lunge feed or accelerate rapidly. Think about the biggest, most complex system you encounter maybe in technology or society or even your own life that has to perfectly balance periods of extreme energy conservation with the need for maximum immediate power output.
That's a challenging engineering problem at any scale.
It absolutely is. And it's a challenge the blue whale mastered through evolution, long before we ever started thinking about it.